All right, so the title or the subject that I was given broadly to talk about was stellar and solar winds. But I'm not a theorist. I'm an experimentalist, and there are some very good textbooks if you're interested in learning about, dust-driven winds and wave-driven winds and exospheric winds, etc. These two books, I think, are the go-to, in my opinion, are the go-to places that cover specifically wind physics. We don't have, in Berkeley, we don't really have courses like this. We have, our stuff is taught in the physics department at Berkeley primarily, and we just teach plasma physics and E&M and classical mechanics and that sort of thing. So we don't have a specific course on this kind of astrophysics. But anyway, I'm going to hijack my hour here to talk about the solar wind in particular, and why it's why I think it's an important kinetic plasma physics problem, why we should be careful using MHD to model it, at least locally. And then I want to talk about the solar probe mission, which Amitabha mentioned already. Not to sound aggrandizing or anything, but I think really if this mission is successful, and we really hope it is, it's going to really kind of set the dialogue certainly for solar wind physics and maybe for coronal physics as well for the next decade or so. We're going to make the measurements that really pin down the physics of this. Okay, so the talk is sweeping and reductionist at the same time. So I'm going to give a little bit of intro to the solar wind, a little bit of history, which is kind of interesting, and then I'll talk a little bit just schematically about turbulent heating. We think that solar wind heating is a result of either a turbulent cascade and some kind of damping or heating process at the end of the cascade, or magnetic reconnection, or some combination of those two. And so it's kind of where we are right now. There are two models that kind of work for solar wind heating. The data is, I wouldn't say contradictory. The data looks compatible with both models at the moment. But I think when we get, the issue is that we're not seeing the in situ heating region, or we're not seeing the hot spots of the in situ heating region, which will be in the inner heliosphere. And so I'll try to make an argument based on the measurements we make at 1 AU near Earth of the solar wind, and into about 60 solar radii, the Helios mission, the German Helios mission from the 70s. Based on those measurements, that what we see when we go closer to the sun will be a more fully kinetic plasma than an MHD kind of plasma. And that the physics of heating is happening there. It's happening in the inner heliosphere. And then we're just seeing a lot of collisional relaxation, or some combination of collisional relaxation and heating. Okay, and then I'll tell you about the mission. I mean, maybe you're not all experimentalists, maybe none of you are experimentalists, but I really think it'll, if we get up on orbit and we get this data, which we're paying a lot of money to do, it's really going to be it's going to be striking stuff. Okay, so you all know this, right? So the sun is a boring star. It's a G-type star that has a black body temperature of 56, 5700 Kelvin, something like that. That's the key thing, right? It's the sun itself, the photosphere of the sun, the temperatures that correspond to the photosphere of the sun are much lower than the temperature of the corona. So the corona, this is an eclipse image. So this is white light, Thomson scattered white light, right? So these are photons, solar photons that have bounced off electrons in the corona, and they're coming at you. So you're seeing the integrated electron density in the sky, in the plane of the sky. And we also know, we've known for a long time, if you just look at this, if actually the next image here is something I grabbed off Wikipedia, you just drop a dipole magnetic field on it, you have to get lucky, right? You have to have the right image of the sun. But the corona is just cosmetically magnetized. It looks magnetized, right? And it is. So we know that the corona is hot and it's magnetized. The scale height associated with the photospheric temperature is very small, right? So if you assume that the temperature of the corona is the temperature of the photosphere, the black body temperature of the photosphere, and you assume that the gas is hydrogen or protons, and you calculate a scale height from hydrostatic equilibrium, you get a number which is 170, a couple hundred kilometers, much too small for what you see in an eclipse image. Okay, so that tells us that something's wrong with that idea. So there's a kind of history behind this, right? So in 1941, Alfven published a paper where he looked at eclipse images and and he tried to estimate, he worked the other way around, he tried to estimate the scale height from the brightness images. And it's a really nice paper, it's hard to find. And he came up with the scale height of a few solar radii, which is more correct, and this suggested a hot atmosphere. So he suggested that the solar corona was actually hot, not the same temperature as the photosphere. So already you see this temperature inversion problem emerging. And then in 1942, Alfven published the first measurements of line emission in the corona of highly ionized iron, which implied electron temperatures of millions of degrees. So at that point, we know that the corona is very hot, and we know it's magnetized. Okay, so these are some diagnostics. This is what we call the E-corona, which emits in UV, soft X-ray. Okay, so Chapman then published a paper in '57, and the ideas were developed primarily to describe the Earth's atmosphere, but he published a paper suggesting a hydrostatic equilibrium. So this is a static atmosphere, so you just have a simple equation of motion, just an equilibrium equation, and he used a collisional heat conductivity, a conductivity equation. So this is a scaling thermal conductivity that scales with temperature in a particular way, and he assumed that all the energy was carried by the heat flux. And he got a model for a static atmosphere, a solar atmosphere, that he published, which was something that people thought about for a while. But it was realized later that if you use measured temperature profiles with this thing, you get a density profile that has a minimum in it. Okay, so it has a minimum at a couple or 100 solar radii or so, and so this would be convectively unstable. So if you have high density on top of the low density region, it'll churn, right? So this told us right away, not us, we weren't born, but it told the people working in the field that that the problem is dynamic. Okay, so it's not a static atmosphere that we have, just a standing atmosphere. It was also the case that this model predicted a pressure that was too high out at the heliopause, at the edges of the heliosphere. There's nothing out there to push back on the atmosphere. So Chapman's model was something that people talked about for a while, but then came Parker's model, and okay, I have an image of here. Now we know, of course, that the solar atmosphere or the corona is very dynamic, right? It's impossible to consider it to be a static atmosphere. So Parker's model is an MHD model. It's actually not an MHD model, sorry, it's a fluid model. It's a simple fluid model. So Parker was motivated by, this is Gene Parker, who our spacecraft is now named after, who's just turned 90 years old, I think, or maybe he's 91 now. So Parker was motivated in part by the work of Chapman. He was also motivated in part by observations of comet tails. So he was apparently working at the University of Chicago, and Ludwig Biermann came by to show these comet tail images to some of the people at Chicago, and in particular to show that the comet tails were split, that there's a dust tail, what we now know is a dust tail, which kind of follows Keplerian orbits. And there's a gas tail, or an ion tail, that points away from the sun. And that ion tail is entrained, we now know that it's entrained in the solar wind, right? So it's picked up by the solar wind and carried away in the direction that the solar wind is blowing. So as a comet goes past the sun, the tail structure splits apart, and Biermann noticed this and published it. And he suggested that there was a wind blowing in the interplanetary space, not just a static atmosphere. And this was a little bit apocryphal. I think the people working at the time didn't believe it. But Gene Parker took it seriously. And so he computed this nice model, which is basically just, you have conservation of mass, you have an equation of state, and then you have an equation of motion that's time steady. So the explicit time derivatives are 0, and you just have the convective derivative. And you can integrate this, if you assume it's isothermal, you can integrate it by hand or with Mathematica or something, and you get these nice solutions that Parker published in 1958, I think. So what Parker's model predicts is that this is the speed of the wind normalized to a sound speed. So again, there's no magnetic field in here, right? This is just a fluid, a single fluid. It's got gravity, it's got pressure gradients, and it's got dynamics in it. And so he found the speed of the wind. He found a family of solutions. This is the distance from the sun in solar radii. And, I'm sorry, it's in a critical radius. It's not in solar radii. And he found this family of solutions, and in particular, there's one solution, this solution, which accelerates as it leaves the sun. It passes through this critical point. This is where it becomes supersonic. So the Mach number here is 1. And then it escapes. Okay, and this is the solution that he proposed would be the solution of a solar wind. So you have a hot corona down here, and essentially it's escaping the gravitational well. The thermal pressure overcomes gravity, and it escapes the gravitational well of the sun and is accelerated out to the heliopause. Okay, so it's a hydrodynamic solution. It's an interesting point, actually. I don't know all the history of this, but around the same time, Hermann Bondi published his paper on accretion, which is basically the inverse. It's the same family of solutions, but looking at inward matter falling in on a star with zero angular momentum, critical points. It's basically the same solution. I don't know who was reading whose archive papers, but they were working on the same thing. So it requires energy input in the corona, and in fact, we know now that the solar wind is heated continuously as it evolves. I have a slide on the nozzle. The problem is essentially the same as well, it's not the same. It has similar solutions as the Laval nozzle, which is the jet engine problem, which I have on the next slide. And when you put a magnetized plasma into this, or when you put an MHD into this, you find also that there is an Alfven point. So the Alfven point is when the wind passes through the local Alfven speed, and it becomes, at that point, super Alfvenic. And those solutions, at that point, that represents a kind of, it's a sort of a discontinuity in angular momentum. In the sense of angular momentum, the plasma inside of the Alfven point is co-rotational with the sun. And beyond that, you have an escaping wind. So it's kind of a causal boundary. Beyond that, there's no wave motion back towards the sun. So that's the important point here, is the Alfven point. I'll talk more about that in a minute. Okay, the nozzle problem, you've maybe all solved this. If you haven't, you should. The de Laval nozzle is a similar problem, but it's in configuration space. So you can think of the Parker solar wind model as being like an escaping gas, but it's a velocity space problem. The constraint on the gas escaping is gravity, and it acts in velocity space. And the de Laval nozzle, the constraint is actually the shape of the nozzle. It's in configuration space. So you have a gas that has some density. There's some cross-section to the nozzle, which is sigma, and some speed. And so this is just says that the flux is constant. And you can take a derivative of that and take an equation of state and reformulate it like this and integrate it. So you just make sigma, the cross-section, be a function of position, and you can integrate it out and get a family of solutions of accelerating gas. So it's a similar kind of problem. And maybe, I don't know, I guess you have a lab this afternoon on solar wind. I don't know if maybe you have something like that in mind. Okay, so eventually this was measured, right? First, actually, by the Russian Luna, I think Luna 1 or Luna 2 probes in the late 50s. They made the very first measurements of the solar wind in a way that they didn't understand, I think, or the measurements were a little bit confusing, and so it wasn't really well understood. But then the Mariner probe, the NASA Mariner probe, made the first measurements getting out beyond the Earth's magnetosphere into the solar wind and measured a flow, a fast, tenuous flow that was essentially cold, a beam that was understood to be the first measurements of the solar wind. So you can look up these papers. They're by Neugebauer and Snyder and Neugebauer from the early 60s, 62, maybe 63. So at that time it was confirmed. It was understood that there's a prediction of a solar wind. There are the comet tails. And now there are clear measurements of a cold, fast beam in the solar wind ahead of the Earth's magnetosphere. Okay, so now we know a lot more these days. I have the next couple plots are from some papers by Steve Cranmer here at Colorado. So this is a measurement of wind velocity, and this is distance from the sun in solar radii. And what we have here is a kind of a collection of stuff. The little open dots are what we call blobs. They're little blobs of plasma, or blobs of white light taken from dynamic coronagraph images of the sun. So you take movies of the sun, coronagraph images, and you can track very small features and track their speed as a function of altitude. And if you do that, you get this kind of profile of accelerating blobs as you go out away from the sun. And we can also use Doppler shift of spectral features of heavier ions to infer the speed of the heavier ions. And we see that in the fast wind, which is hotter and has better spectral features, we see an accelerating profile. In this case, it's oxygen. So there's clear evidence at this point. I mean, it's even much more sophisticated now. The last couple of years, there have been a few papers by Craig DeForest and his colleagues using stereo spacecraft data, and we see very clearly that the white light, the Thomson scattered white light blobs in the inner heliosphere are accelerating outward. Okay, we can also infer remotely and in situ into the helios altitudes something about the heating, right? So if we look at spectral features, the widths of spectral features in line emission, the line emission widths, we can make remote sensing inferences about the temperature, both parallel and perpendicular to the magnetic field, if you know something about the orientations, and we can measure the temperatures and of minor ions in the inner heliosphere. We see large gradients, large, really hot plasma in the inner heliosphere that tapers off. This is Helios data. So Helios, again, was the German mission that went into 60 solar radii. So we see evidence of a plasma that's increasing in temperature to this point, that we have no data in here, and then we see hot plasma in the inner heliosphere. It's interesting, if you look at this bottom panel, I don't expect you to dig into it too deeply from here, but this is showing the ratio, the perpendicular to parallel temperature. So assuming that the outflowing plasma is a bi-Maxwellian, so it's a Maxwellian distribution with one temperature along the magnetic field and one temperature perpendicular to the magnetic field. This is the ratio of those two temperatures, T perp over T parallel. And you see it jump up highly in the inner heliosphere. So it goes into order of 10 or even higher for some minor ions. This has been corrected to show even higher results. And that's pretty huge. That tells you that the stuff is out of equilibrium, right? I mean, if this were H2O, it would be, it could be water looking at it along the field and steam looking at it across the field. So it's a very non-thermal plasma. The solar wind is also, at 1 AU, apparently bimodal. So we think that there's a fast wind, or we've named it a fast wind and a slow wind. Okay, so the fast wind has speeds that are 600, 700, 800 kilometers per second. The slow wind is more like 400, 300. Yeah.
You said that it's very non-thermal plasma, but before you were talking about Maxwell distribution.
Yeah.
So
right. Good question. Good question. So the question is, I said that we were talking about non-thermal plasmas, but I also said that we were using Maxwellian distribution functions. Okay. So in this work, the distribution functions were assumed to be bi-Maxwellian. Okay. But when we start to look at real data, we'll see that it's much more complicated. Okay, so this is a way of reducing UV emission data using a model distribution function. In fact, this is now 10 years old, and people are using kappa distributions and things now that are more sophisticated, right? But the result of perpendicular heating, inferred perpendicular heating, is still pretty clear. Okay, so the solar wind is bimodal. So there's a fast wind and a slow wind at 1 AU, and okay, so the properties of the fast wind are that it's obviously faster, it's more tenuous, so the density is lower, and it tends to be a little hotter. The slow wind is in the opposite situation. In the magnetic field, in the fluctuations of the magnetic field in the fast wind tend to be a little bit higher. Okay, so it looks like there's more magnetic activity in the fast wind. So I want to assert, I mean, this is extreme, but I would assert that this is an artificial way of designating, of talking about the solar wind. In part, it's artificial because the solar wind doesn't know anything about kilometers or seconds, right? It knows about Alfven speeds and thermal speeds and that sort of thing. But it's also the case that when we look at 1 AU, okay, so there are remote sensing observations that suggest that the wind is structured in a way that the fast wind emerges from the coronal holes and the slow wind emerges from the streamer belt. That's certainly true. But when we look at the solar wind at 1 AU, the wind speed is not the best way to order the local properties of the plasma. In fact, it turns out to be the collisionality, the number of collisions. So the Coulomb collision frequency, right, goes like density over temperature to the 3/2. And if you multiply this by an expansion, by a time that we call the expansion time, which goes like 1 AU over V solar wind, you see that all these parameters are parameters that are different between the two kinds of wind, and they vary smoothly between these two kinds of wind. I'll show you a plot in a second here, maybe even next. In any case, there's a kind of bimodal, anecdotally, there's a bimodal nature to the solar wind. In spite of which, the energy flux is constant. So this is a plot from a nice paper by Gaetan-Lechat several years ago. So what we're looking at here, the top panel, we're looking at data from, we can ignore the Helios data on the left side, but we're looking at data from the Ulysses spacecraft and the WIND spacecraft. So WIND is a spacecraft that went over Ulysses is a spacecraft that went over the poles. So it saw, from this last plot, this was Ulysses data, when it flew over the poles, it saw fast wind. This shows the radial parameter here is the speed of the wind. It saw fast wind over the poles and slow wind over through the streamer belt, fast wind over the poles, etc. This is in solar max. This is at solar min. So you see that in this plot. As the spacecraft goes over the poles to high latitudes here, the wind speed is high. The red curve here is high, and then it comes down through the ecliptic plane, and the wind speed is low. It goes down to the southern pass, wind speed is high. So the Ulysses is seeing the speed of the solar wind go up over the coronal holes, over the poles, and wind, the WIND spacecraft, which is at 1 AU in the solar wind in the ecliptic plane, is basically seeing the solar wind, not so extremely fast. So there are occasionally fast wind streams, but it's primarily a slower wind. Okay. But if you instead compute the energy flux, instead of looking at the wind speed, compute the energy flux from the solar wind data itself, you see that it's pretty constant between the two spacecraft. Right? So the spacecraft that's going over the pole, that's seeing fast wind, is basically seeing the same energy flux input as the spacecraft in the ecliptic plane. So this might make you ask if there's, if in spite of the fact that it looks bimodal, there might just be one kind of mechanism, one energy source, rather than different physics at the source. Okay, so what is that energy source? This is a often used cartoon that I believe comes from Steve Kramer. Basically the two models that we kind of hang on to in this kind of Parker-like scheme of solar wind expansion are wave-driven turbulence and reconnection. So in the simplest version of things, the wave-driven turbulence model is such that we take you'll hear, you have heard already about solar dynamo. The dynamo generates magnetic field in the convection layer of the sun, and those magnetic field lines come up. The magnetic field lines that emerge through the photosphere are shuffled around by the convection motion in the convection region. So the boiling motion of the photosphere shuffles those foot points around, and those magnetic field lines launch Alfven waves out into the corona. Okay, so that's one model, and then those Alfven waves have to somehow damp. Okay, and Alfven waves, as you know, if you've studied MHD, are not very efficient at damping, so there has to be some kind of mode conversion process, some kind of plasma wave mode conversion that takes them into a regime where they can damp by Landau damping or some other process. We'll talk more about that. And another model is the reconnection model. This is sort of at base, it's something like the nanoflare or microflare model of Gene Parker. So in this case, you have loops, magnetic loops that rise into the corona, reconnect, and energy is injected onto the open field lines from reconnection, and then you have some subduction again of a closed loop. So basically, we kind of divide things in the simplest way into those two categories. There's also, I'm not going to say anything about it, but there's also a model called an exospheric model, whereby you invoke an ambipolar electric field. Since the electrons are so much lighter than the ions, they can escape the gravitational potential. That sets up an electric potential, and that electric potential pulls the ions out of the gravitational well to create a wind. Those models are, they're interesting. Some of the measurements that support them in terms of electron distributions are viable. I think it's impossible to actually measure the electric potential itself, but that's something that still, I think, is in play, a little bit of exospheric physics. Okay, so there is evidence for Alfven waves. good evidence. These movies, you've maybe seen these before. Maybe I can't make them run. This one on the right is, these are iron. Okay, sorry about this. There's clear evidence for Alfvenic. Like if I could make this thing run, you would see, for example, in here, these little structures, which represent hot plasma and field lines, wiggling around, and if you compute, and you can see wave propagation on those small structures, and if you compute the speed of those propagating disturbances, that speed is comparable to the Alfvén speed low in the corona. And if you compute the pointing flux from that Alfvén wave energy and use some nominal efficiencies, it's comparable to the energy that you would need to accelerate the solar wind. So the model of a wave-driven solar wind I think is viable with some details that are still TBD. So how that would work then is you have the foot point shuffling that introduces Alfvén wave pointing flux. The Alfvén waves propagate away from the sun, and then so at that point you have what is essentially maybe not monochromatic, but a pointing flux of Alfvén waves just away from the sun. So to create a turbulent cascade, which I'll talk a little bit more about in a second here, to take those long wavelength Alfvén waves and bring them down to the kind of short wavelengths that we need to damp on the plasma, like gyro scales or inertial scales, typically you invoke a cascade, a turbulent cascade. So you need something to get that cascade going. You've got pointing flux coming outward, and you need to generate a cascade, you need to have pointing flux coming back, or you need to have Alfvén waves coming back. And there are a few different models for that. One is wave reflection. As the waves propagate in the gradient of the Alfvén speed, they eventually reach a point where the WKB approximation breaks down, and then they reflect. So you have some waves, outward going waves, and some waves that are reflecting back. And those waves can merge together and create a nonlinear cascade. Another model is, and there's support for both these ideas. Another model is that you would have Alfvén wave parametric decay. So as the Alfvén waves grow to larger and larger amplitude, they become unstable to the formation of a backward-going Alfvén wave. So this is just a classical parametric decay process. It's an absolute instability, so it's always growing. And in that model, then you generate the outward-going Alfvén waves self-generate their counter-propagating partner, and that generates a cascade. So the cascade then, which is we'll talk about in a hot second here, takes the energy from the large scales that it's associated with the foot point motion down to small scales associated with the plasma. And at those scales, at gyro scales, ion gyro scales, or at ion inertial scales, you can invoke classical heating processes like Landau damping or transit time damping. So that's a simple model. It may also be the case that in fact, the large perpendicular temperatures that we infer in the inner heliosphere suggest a cyclotron heating process. So that would be a kinetic process that heats by a cyclotron damping mechanism, or perhaps a stochastic heating process. There are very interesting ideas about just stochastic ion heating in plasma turbulence. So it may be that the heating is not simple Landau damping or transit time damping, but it may be some combination of this with cyclotron heating. And there are also models that suggest that the turbulence at these small scales generates its own current sheets. That the nonlinearity of the turbulence itself generates current sheets, and those current sheets can damp in other ways, can transfer energy to the plasma in other ways, including reconnection. So the plasma physics of it is critical. The plasma physics of the cascade and the plasma physics of the damping or heating at the end of the cascade is a critical part, and it's one of the parts that we really don't quite understand yet. There's a lot of motivation for making the right measurements to sort this out. Okay, this heating is kind of continuous. So we know there's heating right at the transition region, right, which I won't talk about, where the helium basically decouples from the photons. But then as we propagate out into the heliosphere, there's continuous heating. So these are results from the Helios spacecraft. So what we're seeing, this is basically a histogram of temperature. This is a plot that was made by Chris Chen a few years ago. This is a histogram of the temperature on this axis versus the position of the spacecraft from 1 AU into 0.3 AU. And so I think Chris has drawn a red line here through maybe the maximum or an average or something like that. Anyway, you see that the profile of the temperatures, of the proton temperature goes like, in this case, minus 0.6. We like to say 1 over R. It's typically like 1 over R, something like that. Whereas if the solar wind were just expanding adiabatically, it would fall off like 4/3. Okay, so we know we're not just having adiabatic expansion. There's heating. There's continual heating going into the solar wind as it evolves outward. And this is a plot that I think was made by Chuck Smith, showing the same thing all the way out to about 80 AU. So this is Voyager spacecraft data, and this is the adiabatic heating profile. Okay, so whatever's happening to heat the plasma continues to happen as the plasma evolves outward. So it's some plasma physics problem. I mean, so what we're measuring at 1 AU even, in principle, has this physics in it. It's just not as pronounced. Am I going too fast? No? Okay. All right, so let's talk a little bit about turbulence. So the classical, and you probably all know this maybe even better than me. The classical turbulent problem is that you have eddies at large scale. So think of this as the foot point motion of the magnetic field emerging from the photosphere, and those large eddies break up into smaller eddies, right? So as you go, so the path of evolution is from large eddies to smaller eddies to smaller eddies, and then in fluid turbulence anyway, you get down to a scale, a kind of viscous scale. So suddenly, that's at the end of it, you've got motion, fluid motion, that's comparable to a viscosity scale, and then you heat the fluid that way. So if you put your arm in the bathtub and stir it on this scale, and then go away and let it evolve to smaller and smaller scales, eventually the principle, the water's hotter. Ignore radiation, convection, etc. Okay, and so the Kolmogorov model for this that you've probably all seen is a very simple one, but it has some powerful predictive power, and that is this model just assumes that the energy rate, the energy transfer rate, so this is energy U squared over some time scale, is constant. So as the fluid evolves from this scale to that scale to that scale to that scale, the energy per unit time is a constant. Okay, so in the Kolmogorov model, the only time scale you have is basically the wavelength divided by the speed. There's no other. It's isotropic. It's a simple model. So you can put these things together. You can stick this time into this conserved quantity, and you get a scaling for the velocity of the fluid with the wavelength, and then you can compute the power spectrum, which goes like the energy per unit wave number, or the energy times the wavelength, and that gives you a prediction that the power in the fluctuations should scale like the wavelength to the 5/3, or the wave number to the minus 5/3 power, right? So that's the whole Kolmogorov argument right there. That the energy transfer rate is constant, and the time scale is just associated with the wavelength of the motion. And that gives you this 5/3 prediction. And if you look in the solar wind, if you look at even the magnetic field, this is not the velocity of the fluid, the magnetic field, you can see a nice 5/3 power spectrum. Okay, so there's pretty simple observational evidence for some kind of cascade process, some kind of turbulent cascade process at 1 AU in the solar wind. But of course, the solar wind is not an isotropic fluid. It's a magnetized. Okay, so this is basically what I said. You drive it at large scales, it cascades down to some small scales. The solar wind is magnetized, right? So this physics is modified by the fact that there's a magnetic field, and so the wave modes in the plasma are different. Obviously, you have Alfven waves, you have fast mode, slow mode, in addition to your pressure fluctuations. And the magnetic field breaks the symmetry of the problem. So now there's a preferred direction in the fluid. It's not just completely isotropic. So in a magnetized plasma, the eddies evolve. So again, we have the evolution in this direction, but they become more elongated along the magnetic field as they evolve to smaller scales. So in the end, you have a smaller wavelength perpendicular to the magnetic field and longer wavelengths along the magnetic field. And So there's a model for this too. There's a model originally, well, maybe not originally, but popularly due to Goldreich and Sridhar, which is a similar thing. So now this model it's basically an MHD model of a turbulent cascade. It assumes that the cascade, that the energy transfer is happening in the perpendicular direction. So it's the perpendicular fluctuations of the Alfven waves that are the nonlinear component, that are carrying the fluctuations. And if you do that, so now you assume the same thing. You say the energy transfer rate is constant, but it's the perpendicular velocity that matters. Okay. Now you have two time scales, because you have your time scale associated with the nonlinearity that you had before, which is this V perp, K perp, but you also have just the simple Alfven wave time scale, right? So what goes into this model is to assume that those two time scales are the same, that the Alfven wave time scale and the nonlinear time scale are the same. So what that says is that this interaction that takes the fluctuations from one scale down to the next scale occurs in one Alfven period. So the Alfven wave just gets one. So this is what's called a strong turbulence model. So this model assumes that the cascade happens rapidly in the perpendicular direction. And if you make that assumption, you have these two time scales. You can do the same argument and get a power spectrum in the perpendicular direction that goes like 5/3. So now it goes like K perpendicular to the minus 5/3. You also get a prediction for the power spectrum along the magnetic field, the parallel power spectrum, and that goes like K parallel to the -2, or like the wavelength, the Alfven wave wavelength squared. And you get a relationship between K perp and K parallel that scales like this. And there's evidence for this too in the solar wind. So, there's a consequence of this. So, if you believe this model, then what happens? So this is K perp. I'm sorry, this is K parallel on this axis. So this is the wavelength or the wave number along the magnetic field, and this is K perp, the wavelength perpendicular to the magnetic field. And if you believe this and you stir the plasma just isotropically at so small K, so that's large wavelength. So you take your stir stick and stir the plasma at a large wavelength. The evolution is in this direction. It keeps the wave number below this limit, this relationship between K parallel and K perp, and it moves the energy along K perpendicular like this. And so the consequence of this, the reason I want to show this, is that this model brings you to, this is log, so this brings you to K perp rho of 1, which is the kinetic scale in the perpendicular direction, long before you get to K parallel rho of 1. This is where the ion cyclotron physics happens, and this is where the Landau damping, etc. happens. Am I going too fast?
No. In about 45 minutes or so, in a few minutes, give them a little break for 5 minutes and then get back.
Oh, so we're going to give them a break now?
No, whenever you are ready.
Oh.
It's a good transition.
Okay, good, perfect. I have a good transition point coming up. Okay, so this model, and I'll show you evidence for this model in a second. This model suggests that the heating process, if the heating is some stochastic plasma physics heating process, it's in the perpendicular direction, not the parallel direction, because the energy reaches the perpendicular kinetic scales long before it reaches the parallel kinetic scales. So that would suggest that the heating of the solar wind is occurring by Landau damping or transit time damping, not by any cyclotron process or something like that. I'll show you the evidence for that. We don't need this. Okay, this is a plot from a paper I published several years ago. This also suggests what's called a kinetic Alfven wave, which is a perpendicular heating process. This figure shows these are magnetic fluctuation spectra in the solar wind as a function of the wave number, K perp, or K times rho, sorry. And this top one is compensated by 5/3. So this is the perpendicular spectrum, and at least over this regime here, it looks like 5/3, nicely like 5/3. And this is the parallel spectrum. And so this thing scales like K parallel to the -2, basically. So these results from a paper by Bob Wicks in 2010 again suggest that the solar wind has a turbulent cascade of the classical kind of magnetized Goldreich-Schrieder style, and that cascade is resulting in heating by probably Landau damping or transit time damping, and that's the mechanism that heats the plasma. In fact, this is from Ulysses data, so this is far out in the heliosphere. Okay, I'm going to talk a little bit about this stuff, and then we'll take a break before we get to the Parker Solar Probe stuff. Okay, so I told you that the solar wind is the distribution functions are not Maxwellian, but let's pretend for a second that they are Maxwellian. So let's pretend that the distribution functions are like bi-Maxwellian. So we have a minus v parallel squared over some v thermal parallel times a minus v perp squared or some v thermal perp squared. Okay, so there's evidence for that in the solar wind. This is, I mean, it's a first approximation. So these are measurements on the left-hand side from the Helios spacecraft. And what we're looking at, the top panel is a distribution function. So this is the magnetic field is along that line right there. And so that's the parallel velocity, and this is the perpendicular velocity across here. And we're looking at a distribution function here at 0.5 AU, so this is halfway to the sun. And in the bottom panel, we're looking at a distribution function at 0.39 AU, so this is closer to the sun. Same format, so you see the magnetic field in this direction. So what do you see? You see that there's a different perpendicular temperature from the parallel temperature, right? So in both cases, the perpendicular temperature is higher than the parallel temperature. And you see that gets exaggerated as you go closer to the sun. We also see here the small component of the alpha particle velocity in the solar wind. Okay, so this can be exploited. This T perp over T parallel can be exploited, or the alpha temperature and the proton temperature can be exploited to explore this whole evolution process. So this panel on the right is from a paper in maybe 2010 or so by Justin Casper, showing data at 1 AU, in the solar wind at 1 AU from NASA's WIND spacecraft. And so these are histograms, so intensity is just the counts of the data. And if you look first at the top panel, this is the ratio of the temperature of the alpha particles. So this is a Maxwellian temperature, a total temperature of the alpha particles, to the total proton temperature of the proton. So that's, let's say a measurement of this peak, the thermal width of this peak, to the thermal width of that peak. Okay, and these are plotted, this axis on the top panel only is the solar wind speed. So what you're supposed to take away from this is that when the speed is low, these two temperatures the ratio of these temperatures is around 1. So these two temperatures are similar, okay? When the speed is high, the ratio gets to be, let's say 5 or 6 or something like that, out like this. And there's a transition, it's a kind of a messy transition here between the two. So this is that low speed, high speed kind of paradigm. The next panel down shows you the same parameter, but now it's plotted as a function of this thing that I just erased, which is, we call on the bottom, we call it collisional age. So this is the Coulomb collision frequency multiplied by the expansion time. So this is basically a kind of measure of the number of Coulomb collisions so we're measuring a chunk of plasma at 1 AU. This is a measure of the number of Coulomb collisions that parcel of plasma has experienced since it left the sun. So it's coming out, it's spending some time evolving away from the sun, and as it's expanding out, it's encountering other particles and it's colliding. So it's had some number of internal collisions during that transit time, and this is a measure of that. Okay, so again, the Coulomb collision frequency goes like the density divided by the temperature to the 3/2. And the expansion time is just the amount of time it takes that chunk of plasma to go from the sun to 1 AU. So it's just 1 AU divided by the speed of the solar wind. Okay, so there's some constants out front here, but that's basically the parameter. And if you look at that, if you use that as a measure instead of just the wind speed alone, you see a really smooth transition from at low collisionality. So the stuff on this side of the plot is basically collisionless plasma. It hasn't experienced very many collisions. The stuff on this side of the plot has experienced some number, finite number of collisions, or some larger number of collisions, actually. This is a log scale during its evolution. And so here we see a nice transition from collisionless to collisionally processed plasma. And what you see is that, in fact, I'll show you in a second, that this transition between these two is exponential. And the reason it's exponential is because the equation of dynamical friction, ddt of, let's say, these parameters, T alpha over T proton, is just minus nu times T perp. Now, this isn't exactly right, but it's approximately right. And the solution of this is an exponential, right? So what this says is that what we're really seeing, we're not seeing some in situ fast wind heating process and some kind of less heating in the slow wind. What we're seeing is plasma that if it hasn't experienced very many collisions, it's hot. So it's made its way all the way from the sun to the earth, and it's got these non-thermal characteristics in it. If it's been collisionally processed a lot on the way out, it doesn't. So collisions are relaxing it and making it more of a simple fluid. And we see this in other parameters too, in the ratio of perpendicular to parallel heating, in the drift between these two species, the velocity along the field line here between the two species, we see a relaxation. So am I getting ready to give you a break? I'm going to go for a couple more minutes, and then I'll give you a break. Okay, so this can actually, this is actually what that dynamical friction equation really looks like. Okay, so if you assume that this time derivative is a convective derivative, is u times ddr or something instead of an explicit time derivative, you can actually take the measurements that you have and integrate them back as though they were close to the sun and predict what the distribution of this parameter would look like back by the sun. So this plot down here shows you the measured probability of that alpha to proton temperature. So there's a peak here, which corresponds to this stuff down here, and there's a gentle peak here, which corresponds to to this stuff. And if you fit them if you assume that there's one distribution that has evolved, this is the distribution from the inner heliosphere, and this is the stuff that's been collisionally evolved, and you integrate it backwards with this differential equation, you can predict a single distribution of hot plasma. In this case, the integration parameter goes back to 0.1 AU. So the two parameters here, I mean, this is basically an equation that looks like, like U, D. Let's call that. Let's put a big delta in here. DDR is equal to minus nu times big delta, and so this is like delta over big delta is like minus nu over u dr, and then you can integrate both sides, and then you start the path integral here starts at the spacecraft, so let's say 1 AU, and it goes into somewhere x naught in the inner heliosphere. And so you can set that parameter and predict what the plasma would look like in the inner heliosphere. So what I want to assert here is that what we see at 1 AU, and I'll show you a couple more bits of evidence of this, but what we see at 1 AU for plasma in the solar wind is not, in a sense, really a bimodal kind of plasma. It's not like there are two kinds of plasma in the solar wind at 1 AU. There's plasma that has evolved collisionally, that's been heated, that's been processed kinetically, and it's evolved collisionally as it propagates out. And so we see a mix of this depending on these parameters. And this is important because this is predicting now the fact that we can use this. It predicts what we're going to see in the inner heliosphere. And this is Justin's most recent paper on this, where he actually makes a prediction for this heating zone. So this is basically the model that when you're close to the sun, okay, very very low in the corona. Actually, at the photosphere, the plasma is again collisional. But then you have a corona and you have a lot of heating, and at some point the heating shuts off, and then beyond that you just have collisions, and the collisions are relaxing the plasma, making it more Maxwellian. Okay, and you can integrate this equation back and make a prediction for where that boundary is. We see this as well in the electrons. So the solar wind electron distribution has three populations in it. Well, approximately three populations in it. There's a cold, what we call the core, which is pretty Maxwellian, and in fact it's largely, there aren't large temperature anisotropies in it. It's very collisional. It's probably 95% of the density at 1 AU. It's about 10 eV of thermal temperature. We see a population that we call the halo, which is kind of kappa-like, and it can be very anisotropic, perpendicular and parallel to the field. And then we see a population that we call the Strahl, which is a German word for a beam. And the Strahl is basically what we think is our coronal electrons, and they propagate along the field line. If you look at the properties of these, okay, so this is a distribution function, an electron distribution function in the solar wind at 1 AU. And I guess what I want you to look at is this plot on the right. This is the parallel velocity. So this is a cut in the parallel direction. And you have this cold, dense population at low energies. You have these tails that are kappa-like out here. And then on top of it, you have this kind of beam that we call the Strahl. So this is, again, at 1 AU. You can do the same kind of arguments. You can look at this is a measurement of the heat flux in the solar wind at 1 AU as a function of, let's say, collisionality, distance from the sun. So on this side of the plot, we have what the plasma would be like close to the sun. On this side of the plot, we have a collisionally processed plasma, and what we see is that the heat flux is, this is a model called Spitzer-Harm, is collisional here and not collisional here. And we also see drifts. So these two populations, the core and the halo, they drift with respect to one another along the field line. So they're not flowing together. The halo is faster and it's escaping and it pushes the core backwards a little bit. And we can see that velocity between them. So this is now the velocity between those electron populations normalized to the Alfven speed is a function of this collisional parameter too. So the more collisional the plasma is, the more it looks like you have one population of electrons. The less collisional it is, you have two clearly distinct drifting populations of electrons. It's kinetic. This side of the plot is kinetic. That side is not. And again, you can just use the equation of frictional slowing, integrate it back to the sun, and you find that at about 0.1 AU or so, close to the sun, you're in this regime. You could run this curve all the way out here, and you're in this regime where there's a large drift between these populations. So, am I at my punchline yet? One more set of observations to the punchline, and then we'll take a little break. Okay, so this is a recent work by Tim Horbury, and what he did was look at, so this is this Helios spacecraft at 0.3 AU, the WIND spacecraft at 1 AU, and Ulysses spacecraft at 2.4 AU. And he's looking at high-speed solar wind. So this is the fast solar wind, and this is just the radial velocity, the outward velocity of that plasma. And what you see is that when you're far from the sun, it looks pretty steady, right? This is 2.4 AU. It's a pretty steady wind. When you're at 1 AU, it's more variable, but still relatively steady. And when you get into Helios, if you fully resolve, or not even fully resolve, if you have as high a resolution as you can get in time from this Helios data, you see a lot of spikes. Okay, so the wind, even the fast wind here, looks very spiky. There are these spikes in the radial outward speed, and you can even zoom in on them. This is zoomed in on one of those spikes down here, so you see the wind speed goes from 700 or 800 kilometers per second up to 1,000 kilometers per second. So it's a very fast, impulsive spike of plasma at those altitudes, associated with a little turn in the magnetic field that in fact looks like it's an Alfven wave. It looks Alfvenic. So this would suggest that even what we think of as the homogeneous fast wind, when you get into the inner heliosphere at 0.3 AU, in this case, is impulsive. It's spiky, and it has Alfvenic-like structures that could be waves. They could be some kind of jets from low in the corona that we're measuring at those altitudes. So, okay, so this is where I'll stop and we can take a break. But the question here is, what can we expect to measure in the corona? I think we have clear evidence that there will be large anisotropies, perpendicular to parallel temperature anisotropies in the plasma. We think that the heating of the plasma is occurring in the inner heliosphere. There will be large non-thermal electron populations and drifts between the electron populations. And there's evidence for impulsive Alfvenic structures and waves. And so the point of this, the first part of this talk, is that the solar wind at 1 AU is considerably heavily processed by its evolution, by collisional evolution and turbulent evolution. And as you get into the inner heliosphere, what we're going to see is something that is much more exotic, much more kinetic and structured and impulsive. It's not going to be a simple fluid picture like we have at 1AU. Okay, so Amitabh, can we take our break now? Okay, so let's take a break for 5 minutes. Is that right? Well, yeah. Okay, we'll come back at 9:30. I'll give you 8 minutes. Okay. You're all physics students, right? More or less? Yeah.
Some engineering.
Some engineering too. So, but you know about distribution functions and stuff like that. Okay, good. I assumed that, but.
Is there any correlation between the collisional age you said and the solar wind speed?
The solar wind speed? I mean, just this here. There's this one over. I'm going to turn this off. I think we're going to find with solar probe, which I'll talk about in a second, I think we're going to make kind of the same. Before the fast spacecraft, people really thought about the aurora as a simple fluid. The model of the fluid is fast, show that it's all full of potentials, Strahl structure, plasma structure, a lot of the physics involved. Should we go again? Yeah, let's go. Okay, so in the last little bit of the talk here, I want to talk about solar probe. Since, and again, I think it's something we have to talk about because assuming we're successful, it's gonna be, like I said, I think it's really going to set the dialogue for what we do in solar wind physics for the next decade. So this is a little picture of solar probe. Okay, so solar probe, I'll talk to you about the science and the mission and the instruments a little bit, everything. So the solar probe mission has these top-level 3 science goals, science objectives, and they are on the left-hand side there to trace the flow and energy that heats and accelerates the corona. So basically, what's the physics behind coronal heating? To determine the structure and dynamics of the plasma magnetic fields at the source of the solar wind. So what's the structure of the corona? What's the plasma structure of the corona? And then 3, to explore the mechanisms that energize energetic particles. So we see energetic particles associated with solar flares, with CMEs, with structure in the solar wind. So to explore that as well. So those science objectives map into some measurements, and the measurements map into 3 instrument suites that we'll talk more about. Okay, so what do we expect to see? Okay, I tried to make, in the first part of the talk, I tried to make the case that what we're going to see is a kinetic plasma, not an MHD kind of plasma. Okay, so we're going to see large temperature anisotropies. We're going to see large drifts between the species. We're going to see impulsive magnetic fields, waves. It's going to be a very dynamic place in the inner heliosphere. Okay, but to design instruments, you have to kind of have to go beyond qualitative things like that. So if you look at what we know about the solar wind, this is the density, the magnetic field magnitude as a function of altitude, radius from the sun. This is the solar wind speed. This is the solar wind density. This is the solar wind proton temperature, all as a function of distance from the sun. So we have these measurements from the Helios spacecraft, and we have some models, which are listed here in the little color bars. And so we can what we've done is take the measurements from the Helios spacecraft and fit them to various models and constrain them by some other things. And so you can make a prediction. These bars here, but this dotted line and that dotted line, the two leftmost dotted lines are the primary science orbit of Solar Probe, which you'll see more about in a second. Anyway, we can make predictions for what the magnetic field intensity would be like, what the solar wind speed would be like, density, temperature in the inner heliosphere. And we need those predictions to decide what to measure. So if we take those predictions, these are some parameters: the magnetic field, the electric field, density, temperature, solar wind speed, Alfven speed, and some plasma frequencies, gyro frequencies, and then these are convected spatial scales. So this is the time it takes for a Debye scale to pass the spacecraft, or an electron inertial scale to pass the spacecraft, et cetera. We can compute those so these are 1AU values, and we can use those models to predict what we should be seeing in the inner heliosphere. Okay, so we'll see, at the Solar Probe altitudes, we'll see thousands of nanotesla magnetic field. And if we have a delta B over B of order 1, we'll have fluctuations on the order of thousands of nanotesla. The density should be several thousand per cc. So whereas at 1AU, it's order of 10 per cc. We expect kind of 100 eV electron temperatures. Okay, so all those things then let us compute these timescales associated with natural motion in the plasma or convection of stuff past the plasma. And what we see is that these are very, very rapid timescales. Okay, so to measure a shock, the typical scale size of a shock is what we call a convected ion gyro radius. At 1AU, that takes on the order of a second. If you make several measurements per second, you can measure the structure of a shock. But at Solar Probe altitudes, that's on the order of milliseconds. So when a shock crosses the spacecraft, it will require sub-millisecond measurements just to see the structure of the shock at all. So the point is that the solar wind, the measurement environment in the solar wind in the inner heliosphere for Solar Probe is much different than it is at 1AU for this wind spacecraft that we've been using, for example. So we need to make measurements fast. We need to have large dynamic range. We need to measure large values, fluctuations of values. And so this isn't impossible. It's not even actually that hard. It's kind of like the auroral region, but it's different from what we're accustomed to. So that's a big consideration. This is the baseline orbit for Solar Probe. So the launch was scheduled for July 31st, 2018. We've had a couple delays. We had a delay to, was it the 6th, I think, either the 4th or the 6th? That was due to a problem with purging the third stage. I'll talk more about that in a second. And now we had a delay this last week, which is due to, actually it's funny. So the spacecraft is built up on top of a third stage, which is a booster rocket. And then this whole thing is encapsulated by a fairing. So there's a nose cone that goes up, two sides that go up and glue together at the top. And they noticed I think it was on Sunday, so there are some portals. You can look into this thing and stick your hands in and do some things. But it was noticed that there were strips of foam, like weather stripping basically, sort of little strips of foam that were dropping out of the nose cone onto the spacecraft. And they didn't damage anything, but it was decided that the fairing had to be taken apart again to fix this up. And so taking that big fairing apart costs a couple days. So we have another delay. So our launch date now is August 11th, which is, I guess, 2 weeks from Friday. So it's coming up very soon. Okay, so the mission design is like this. We launch, let's say, on August 11th, and we have a Venus encounter a month later or so. And so here we encounter Venus, and we do, the spacecraft has hydrazine thrusters on it, and so we do a burn of those thrusters and change the angular momentum of the spacecraft. And that brings the first perihelion pass down to about 35.7 solar radii. So that's from the center of the sun, so 34.7 from the photosphere. So that first perihelion pass is on or around November 1st of this year. So that's soon. And in fact, our mission operation scenario has us getting some data back, a few gigabits of data back in early December. So we're hoping that we can actually come to the AGU meeting in Washington, D.C. in December and show what this first perihelion pass looks like. I'm hoping that I'll be able to show you the magnetic field of the solar wind at 35 solar radii. Okay, so then we have, it turns out, 6 more of these Venus gravity assists. So there are a total of 7 Venus gravity assists. Each time we burn the thrusters, change the angular momentum of the spacecraft, and that drops the perihelion down on the next pass. And after the 7th one, we have our first minimum perihelion at 9.86. So that's, in principle, the closest we get to the sun. And again, that's from the center of the sun, so 8.86 from the photosphere. And that occurs in 2024. So that's basically the mission design. Oh, and I should also say that this, when we're at this perihelion altitude, the spacecraft's Keplerian velocity is almost 200 kilometers per second. So at that point, I mean, people are saying anecdotally, I don't know how one would verify this, but that solar probe will be the fastest ever object made by humans. And if you look back at those plots I showed you of what we expect the solar wind speed to be, the solar wind speed itself at that altitude will be comparable to a couple hundred kilometers per second. So that means that if you're riding on the spacecraft, the wind is going to be coming in at a 40-degree angle or something like that instead of coming out radially because of the aberration. The speed of the spacecraft is so high. So it's a really new environment for this kind of physics. This is a little movie that Terry Kuchera made. So here you can see. Yeah. Please do, yes. Yeah, that's great.
This is a mission that has been in the making for, I don't know, 50, 60 years, ever since we knew that there was a solar wind at that point in prophecy or in solar wind. What I want to go back to is how long we have been working on this mission. So I've been at NASA headquarters since 1980, and I've been trying to get this mission on since 2000. We came very close, I think, in 2003. The mission was almost ready for selection, the Bale, and it got cancelled accidentally, actually, by Congress, because they were trying to cancel some other stuff, like Laval, and solar probe was caught in that mix. And they wouldn't go back. Even though we had the money, they made a mistake and they were not going to take it back. And solar probe was just cancelled like that. And it was never happened for a long time. And this is, you can just see how iconic this mission is. This is something very different from any other mission we have done, because we are going to a star. And that's fundamentally the environment. So the AA, Associate Administrator, was very encouraging and said, we're going to find some initiative now and we'll do this mission. And administration changes. We go through Republican Democrats and different people. And mission like this is actually caught into that turbulent environment, much like the solar wind turbulence. And it just went on. In 2007, we had a new associate administrator who is from Boulder, Alfven. Many of you know him. He was actually in my graduate school year. I was in Boulder for 3 years. He was my office mate, so I knew him very well. He somehow was able to do the Pluto mission out of sync, though all 3 missions were cancelled. Europa still hasn't happened. And so I used to take a look people, why go to a dead planet when you can go to a new star? And it was a joke between us. So when he became the AA, I never even thought about it. Came to my office, gave me a hug, chatted, and as we came up, there was a 1/10 model of solar probe, a different solar probe. I'm giving you the story because you see the evolution of the idea of this simulation. That's why it was renamed solar probe class. So this 1/10 model had a cone. It was like an umbrella cone shield, and all the instruments would be underneath. And it was actually a 1/10 model. And I just looked at it and I looked at it and I said, Alan, if you make this 10 times bigger, we have a solar probe mission. Let's make this happen. And this concept that you're seeing now happening during Alan Stone's 1 year at NASA headquarters, we had the last definition team for solar probe, where as I was reading the definition team, I never imagined I myself thought was going to do it. But the community would come together to do this eclectic mission. Solar probe was always to go to the pole to get the pristine high-speed solar wind, to go solar radii for 10 hours of data. So this concept of flyby so many times and increase the amount of data, I don't know, by 10, 20-fold, we did not think it was possible, even as we were doing the science definition team. And you can see what an extraordinary mission this is, that everything that science definition team is just going to give us so much more information than we had from the previous one. So I kind of wanted to share this, just seeing this is bringing back, and this wasn't easy. It took a lot of effort, time, arguing to figure out what's the right thing to do.
Yep.
And I have some stuff.
You have some
You guys, I don't have many, so I'd like to actually hand it out.
some swag.
If I run out, and these are solar proof things and
Good.
just
Thanks, Lika. Thanks. I mean, I should say, so there have been many, masters of the solar probe concept over the years, but Lika is the mother of Solar Probe Plus. I mean, I think this happened because of her persistence and her devotion to it, her dedication to it. Okay, so here's a plot that just shows the orbit dynamically. And we were looking at this because we were looking at the position of the stereo spacecraft, which is here. This is stereo A. Here's Earth, Venus, Mercury, and there's Solar Probe. So it maybe already had a Venus encounter, but you'll maybe see another Venus encounter where it changes its perihelion altitude here in a second. Anyway, we're going to use stereo. We'll use assets on Earth, et cetera, to support Solar Probe through its lifetime. There's a Venus encounter there. Do I have that in there twice? Okay, so there are instruments. And a lot of people have moved around and become professors since we were selected. I think we were selected, was it 2010, Lika? Well, the instrument selections were in 2010, I think. Yeah, so we've been working on the thing for a long time. So there's a set of instruments that my group is leading, which we call fields, and we'll measure the magnetic fields, both the DC magnetic field and waves, magnetic field waves. We also measure electric fields and radio waves and plasma waves, and by inference, we can measure the plasma density and temperature. It's a pretty versatile suite. There's a suite of energetic particle instruments that's led by Dave McComas at Princeton. So this will measure the energetic particles associated with solar flares, with shocks and CMEs, and some of the sort of not thermal but ambient energetic particles as well. There's a set of instruments that's called SWEEP, solar wind electrons, alphas, and protons, led by Justin Casper at Michigan. And that is an instrument to measure the thermal plasma. So there's actually three or more sensors, three sensors that measure the thermal distribution functions of ions, electrons, protons, alpha particles, electrons, and some minor ions as well. There's a white light imager. I think I maybe have a movie of this, which is called WHISPER, led by Russ Howard from NRL. And so this is a camera that measures white light, again, Thomson scattered white light. So it's measuring plane of the sky electron densities looking in the direction that the spacecraft is moving. So as we fly past the sun at 200 kilometers per second, this thing is going to be looking in the direction that we're moving. So it'll see the stuff that comes at us. And it looks from down to about, I think, 2 solar radii. So it doesn't look directly at the sun. That would saturate. It looks to about 2 solar radii and then out to where the Thomson scattering cross-section falls off, where it gets dark. And then up and out of the ecliptic by, it's like a 70-degree field of view like that. So what you'll see in that thing, and I think I have a slide from that, a simulation of it. And then we have a kind of a lead scientist, an observatory scientist, Marco Belli at UCLA. Yeah, here's the WHISPER thing. So this is kind of a simulation of what that imager might see as we fly through, streamer structure in the ecliptic plane. So we'll see this stuff in the camera, and then we'll measure it coming over the spacecraft with the in situ measurements. And then, of course, we'll use other assets to measure things from the ground or from stereo or other spacecraft. that's what the spacecraft looks like roughly. That's an old picture from 2015, but it mostly looks the same. This is a drawing of it, of course. So there is a heat shield on the top, which is about, I think it's 2.7 meters across, and the heat shield is a kind of carbon composite. It's basically a carbon-carbon cup that has a kind of foam in it, an aerogel, which is a carbon foam, and then on top of it is a ceramic faceplate. And that thing takes about 1 megawatt of solar flux at perihelion, and it heats up to about maybe 1500 C or so. So it gets very hot. Behind that, so this is the actual spacecraft down here. This is a set of radiators. Those radiators everything behind this heat shield, almost everything behind this heat shield, only sees the black of space. It doesn't see the sun at all. So this heat shield casts a shadow back here. These are the solar panels that are folded up on the side, and the tips of those solar panels actually see sunlight at perihelion. And so they're actively cooled, and they provide the energy to keep the battery charged as we go through perihelion. And then when we get out of perihelion, far from the sun, those solar panels can gimbal out and take sunlight to charge the batteries again. So there are these radiators that we actually pump water through to radiate, and it's interesting. The things they're so efficient that at 1AU when we launch, 2 weeks from now, we keep the water in a tank inside the spacecraft. Otherwise, it would freeze because it would radiate away all of its heat and freeze in these things. So we have to keep the water in a tank. And as we go towards the sun on that first inbound pass, we tip the spacecraft sideways and warm up these radiators one by one with sunlight, and then fill them with water after they're warm, so that we can keep the thing from freezing up. What else can I say about it? It's about 3 meters high. I mean, the spacecraft itself is it's like a big barrel, about like this lower part here. You could almost put your arms around it. It has some articulated doors that you can open up and get inside of and work on. Okay, so and I want to say also that this has to be the heat shield really has to be pointed at the sun all the time through perihelion. So we have a nice closed loop attitude control system that uses the thrusters and momentum wheels, and it has a set of star trackers to image the star, so it knows the orientation and attitude in space. And it has limb sensors that sense any sunlight that comes over the edge of the heat shield, and it uses all of that in a closed loop system to keep the thing pointed through perihelion. So we're not commanding it as it does this. It's all autonomous. So it's a different kind of mission than we've worked on before. This is kind of how some of the payload is accommodated. So there's the heat shield again. So this is my instrument suite anyway. Has these 2 flux gate magnetometers, which measure the magnetic field up to a couple hundred samples per second or so. So through sort of the scales of the larger scales of shocks and current sheets and that sort of thing. And they're on a boom behind the spacecraft. This is a boom that is articulated, so this leg of it folds up against that, and then the whole thing folds against the spacecraft for launch. And then at the end of it, we have an induction coil, a search coil magnetometer, which measures high-frequency magnetic fields. It's interesting, actually, that this stuff on the boom in the back has to be heated. We have to put heaters on those magnetometers to keep them from breaking apart because it's so cold. The materials, differential expansion of the materials would crack them up. So the stuff behind the spacecraft can get very cold. And we also have these antennas that are hard to see in this image, but they're 2-meter long antennas that extend out in 2 pairs so there are 4 of them, and they make 2 orthogonal pairs to make a kind of dipole, 2 cross dipoles to measure the electric field. And those things sit out in full sunlight, and so that was kind of a challenge. We had to find refractory metal that we could machine and bend and work with that would survive temperatures of 1400 C and operate as a sensor. But we found a nice, we're using a reactor-grade niobium alloy called C103 niobium that we could buy in tubes. They're 1/8-inch diameter tubes. And then at the bottom of it is a kind of, I don't think I have a picture of it, but there's a kind of rig to hold it and thermally isolate it from the spacecraft. So at the tip, these things are 1300 C. As they tuck behind the heat shield, they get down to a couple hundred C, and then we have a preamp at the base, an amplifier, which runs at a little bit more than room temperature, 40 C or something like that. All the stuff on the spacecraft, doesn't really ever see any temperatures greater than 40 or 50 Celsius. That's our test limit was about 50. So it's a really heroic thermal engineering effort. The plasma instruments are back here in the shadow behind the heat shield, with the exception of the Faraday cup. So this Faraday cup is an instrument. It's a kind of retarding potential analyzer. So it measures a current as a function of energy, and it's pointed right at the sun too. So it's looking right at the sun, measuring that solar wind beam that comes right out, trying to measure the energy distribution of the solar wind. So that thing took a lot of really special thermal engineering to achieve as well. So we put a lot of effort into designing these things, in particular the things that stick out in sunlight, and to make them function as good sensors. Yeah? Say again? Why the what? The two? Why two magnetometers? Good question. Well, nominally, two magnetometers to calibrate out the spacecraft magnetic field. So the spacecraft, for our instrument, the instrument that measures electric fields and magnetic fields, having a spacecraft there is bad news because the spacecraft is full of current sources and switches and chopping power supplies, and these are all sources, and permanent magnetism as well. These are all sources of noise and pollution to our measurements. So in principle, when we proposed, we put the two magnetometers on so we could measure the spacecraft field here and the spacecraft field here and then remove it and know what it was. But it was kind of later realized that the magnetic field measurement is so important on the mission that we should make it kind of redundant. And so we took the architecture of our instrument, we made it not fully redundant, but we made it kind of two-sided architecture. So we have two power supplies, two processing units, and one magnetometer attached to each side. So if one of the power supplies fails, we've got the other one to go. So we're the only instrument on the spacecraft we're not called redundant, we're called enhanced reliability. Yeah, it's an interesting point. So the intent is to do the radio astronomy, the solar radio astronomy that we're going to do with this thing. We need to measure electric fields that are sort of microvolts, fluctuating electric fields that are on the level of microvolts. And the spacecraft itself is full of this kind of noise. You put a laptop computer next to my instrument and it'll just light up, So what we did was we required that all of the power supplies on the spacecraft, on all the subsystems, operate at fixed frequencies. So that they're chopping power supplies, they're cycling power supplies. So we have a set of frequencies that they can use, and they have to use crystals on their power supplies to control that frequency, to keep it right on the button. So the spacecraft is full of noise, right? But we know where all of it is in frequency space, and so we can mask it out, we can measure around it. But all this stuff has been really very challenging. What time is it? I think I can skip over this stuff. So our operation scenario is like this. We have what we call a solar encounter period, which is between 0.25 AU and whatever the perihelion is. So this tends to be something like the order of a couple weeks. So our science requirement is that we operate inside of that distance. So we're required to make measurements inside of 0.25 AU. So for basically, a week before and a week after perihelion. Okay, so in practice, we're going to, of course, try to make measurements over as much of the orbit as we can. And it just really depends on power, on how much power we have. You can't run the solar panels on the spacecraft were sized to produce enough power to run the instruments inside of this orbit. And so if there's extra power, or if we turn off one instrument or another instrument, we can maybe run over the whole orbit. And then, of course, there's a finite amount of data that we can bring to the ground as well. But there are 24 solar encounters. At the end, when we're down at that low altitude, our orbital period will be about 88 days, about 3 months. So it's really going to be like a campaign-driven thing. We're going to take data, get that data down, look at it, figure out how to configure the instruments again. We have to do some manual selection of the data because we can't bring all the high-resolution data to the ground, and then it'll dive in again for another pass. And I think this is my last slide. So these are actually pictures that I took with my own iPhone about a month ago. So this was the spacecraft in the clean room at a place called Astrotech down in Florida before they put the heat shield on it. So all this red tag stuff comes off. There's the Faraday cup instrument up there. You can see those red tag things are our electric field antennas. These are some red tag things on the energetic particle instruments. Anyway, the heat shield later went on top of that. The solar panels aren't on here yet either. But I did get to go stand next to it about a week ago, fully configured for flight with all the red tag items off of it. It's just majestic. Okay, and that's our rocket. We're launching on a Delta IV Heavy, which is a big a big rocket provided by, it's a Boeing rocket actually, provided by ULA. I've updated this to say our launch window is not earlier than August 11th, but that's coming up pretty quickly. The spacecraft is all together. The ground systems are ready to go. We had what's called KDPE, Key Decision Point E, where we got the green light on the spacecraft side of things that everything's ready to go. Right now, as I said earlier, they're integrating it onto the third stage. So it goes onto a third stage booster, and it was on that a couple weeks ago. Then they had a problem purging the third stage, which they took a couple days to fix, and then they have this problem with the foam, the weather stripping, that they're fixing now. But the plan is to roll so the third stage and the spacecraft and the fairing are all one unit, and they're at this Astrotech place, which is across the causeway from Kennedy Space Flight Center. The plan is to roll it across the causeway on the 31st, which I guess is next Monday. So on Monday, if they stay on schedule, at midnight or something like that, or 2 in the morning, they'll get a police escort and open the gates at Astrotech and drive the thing across the causeway into Kennedy Space Center and take it out here to Complex 37, which is where the rocket is, and then they'll start to integrate it onto the rocket. So it's all coming along. It's all happening really quickly. And I think that's my summary. There's one point I'd like to make here at the end. So my summary is this, that the inner heliosphere is obviously the birthplace of the solar wind. The conditions there, I think, are likely to be very kinetic. The plasma that we're going to see there is going to be a kinetic plasma with a lot of transient activity in it. So there'll be large pressure anisotropies. There'll be non-thermal particle populations, drifts between the species, structured turbulence, developed turbulence perhaps. Solar probe is designed to go inside the Alfven surface. I didn't make that point. We're designed specifically to go inside the Alfven point to enter into the region where the solar wind is subalfvenic, where we're kind of in the corona rather than the solar wind. But I also want to say that there's a lot of other stuff happening at this time. There's Solar Orbiter, which is a European Space Agency mission with similar science. It has a bigger suite of remote sensing measurements. There's DKISS, the telescope in Maui that you maybe know about. SKA, the Square Kilometer Array, is making radio measurements of the sun. All these assets are coming online at the same time, basically. And if you rack all this up, this is like, probably $3 billion worth of investment in coronal physics. So it's a big deal. It's like, it's like building the LHC to find the Higgs, or, like a Mars sample return campaign or something like that. It's a really big deal. There's a lot of assets going into coronal and solar wind physics. And so now's the time to work on it. So you're all in the right place, doing the right thing. So, I think the next decade or so, there'll be really a lot of interesting, exciting work in this field. Okay, that's all I have. Yes?
I have a couple questions.
Sure.
So first, in terms of the spacecraft, so I think this is an issue for all spacecraft, but it seems like the space weather aspect of detriment to a satellite is going to be much higher the closer you get. And I mean, this is supposed to be detecting particles and other things. You don't want to turn it on because that's what you want to detect.
Yeah.
But you also want to detect.
It turns out to actually not be that bad. It's not that bad. I mean, so you would spec this in terms of kilorads behind some amount of aluminum or something like that. And the radiation environment associated with like solar energetic particles is not. First off, we don't actually think we're going to see that many big CMEs. If you just convolve the spacecraft orbit with the expectations of the occurrence of CMEs, we don't think we're going to see that very many big ones. But it turns out that that radiation spec doesn't really drive the things. In fact, what Lika was talking about earlier, the older version of Solar Probe that was supposed to go over the poles, that mission was going to go to Jupiter. It needed a gravitational assist from Jupiter to get up out of the ecliptic, and that is a nasty radiation environment. The environment of Jupiter, the energetic particle environment of Jupiter, of trapped radiation, is the worst in the solar system. So that mission was really driven by radiation requirements, but it's not so bad for us. We should be able to see all this stuff, measure it.
So you can talk about there being two potential energy sources.
Yeah.
Connection and
Mm-hmm. That was a really reductionist viewpoint, but yeah, I did say that.
Yeah. So, but you mainly focused on waves and turbulence.
Mm-hmm.
Is there any reason why they wouldn't both?
No, they're probably both operative. Yeah, I mean, in fact, there's clear evidence of reconnecting current sheets in the solar wind at 1 AU. And I expect as you go into the inner heliosphere, beta is lower, there's more parameter space open for reconnection. So I think probably, I would guess that reconnection will play a major role too. I just talked about turbulence because it's my thing.
But is the reconnection something that's also going to...
Yeah, the instruments are designed specifically to resolve the spatial scales of reconnection in the inner heliosphere. And we also have, so I mentioned that we have this solar radio measurement that we make with the antennas. And the idea of that is to see a kind of radio burst that's called a type 3 solar radio burst, which is associated with flares. We see it associated with big flares at 1 AU, so it's a reconnection, electrons injected onto the field lines radiating. If these kind of microflare and nanoflare models of heating are important, we should see a kind of a background of small bursts like that arise as we go closer to the sun. So we're specifically trying to measure that as well. Yeah. Well, that's a good question. People argue about this all the time. I mean, okay, in a simple-minded way, you could take, some interval of magnetic field data, vector magnetic field, right, and find the average direction of the magnetic field in that, and then rotate your fluctuations into that coordinate system, and then compute a power spectrum along and perpendicular. And that's been done. People still do that. But in fact, to be really consistent with a model like Boulder or Sridhar, you have to do that kind of local in wave number. So you take an interval of data and do that for some large scale fluctuation, but then when you want to go to a smaller scale, you have to choose a different interval to compute the average magnetic field. The average magnetic field is scale dependent as well as the fluctuation field. But there are routines for doing this. You can take some wavelet decomposition of data and do scale dependent rotations and that sort of thing. Well, another point of this actually is, in all of this, we assume that we're measuring, that the time series that we're measuring is actually a convected spatial, that we're measuring a spatial measurement that's convected past the spacecraft. And so we use a fixed speed typically to convert the time into space. So you can compute a wave number. That will be trickier in the inner heliosphere. It's not clear at all. The wind speeds will be lower. It's not clear, and the Alfven speed will be higher. So that might not work in the same way. So it's a non-trivial kind of thing. Any other questions? Amitabha. Yeah. Mm-hmm. Yeah. That's a very good point. It's not just reconnection associated with flares. It's reconnection that's being self-generated by the turbulence, or current sheets that are being self-generated by the turbulence that may reconnect as well and provide heating, damping. All right, should we have coffee?